Okay, so trapezoid representing this information says that, well, let's let the altitudes be number of millimeters squared per second. This is a thing like independent variable and dependent variable. Okay, the independent variable, the thing you have control over is the R's that you're going to use, the radii, and the flow rates follow from the radii. So the thing that follows from the radius, of course, this radius is 2 millimeters, and this radius is 3 millimeters. And when you have that kind of information, it's always good to write it down. It's not really part of the trapezoid, but it's a reference that helps you understand exactly where you are and what this means, right? And you want everything you can because it's often really difficult to interpret meanings, okay? That's really one of the central things in an applied calculus course. It's also important in just a theoretical calculus course because it gives you perspective, but especially in this course. We're big on meanings, okay? Big on interpretations. Okay, so we have all this information. Well, everything is really easy. Obviously the slope is 0 because you have 0 rise. And we should technically list left altitude, right altitude, et cetera, right? But as long as we're sure we've got everything, we're going to, just in the interest of time, we're going to kind of skip some of that labeling, some of that documentation. So we got 0. The average altitude, well, the altitudes are the same, duh. So the area is going to be the width times this. Well, that turns out to be 19.2, right? And what are the units?
Millimeters cubed?
Yeah. Per second, right? Okay. So really, slope of 0 just tells us that on the average between these 2 points, there's no change in the in this flow rate per unit of radius, right? Now here we have units of radius. So what we have is like this. Here's our and up here we have flow rate per unit of radius, right? So when we multiply them, flow rate per unit of radius times unit of radius just gives us flow rate, okay? Okay, so we conclude that the rate at which blood is flowing between radius 2 and radius 3 millimeters. So let's look at a cross section here, okay? Here's the center. Here's radius 2 millimeters. I don't have room to write the millimeters, but I'll do it anyway, but you can't read it, right? And 3 millimeters. Choked in that circle toward the end. So there's not a good place to label that, but I'll just say 3 millimeters. And we understand this. That's the amount of blood that's coming at you if you're looking head on into the flow between here and here. So it's blood, so let's make it nice and red. It's coming at you, so there's a blue shift due to Doppler, but it's not coming that fast, so you can't observe it, so it's still red. Okay, forget what I just said. Yeah, gravitational redshift of galaxies and stuff like that. If they're coming at you, they shift toward blue. Okay, it's not a galaxy. It's not moving nearly that fast relative to us. Just a few millimeters per second, right? Okay? That's how much blood is coming through this much of the artery, right? Okay? No big mystery to why that might be important. Okay? Well, now we could do that between 3 and 4 millimeters, so we get this part of it. And between 0 and 1 millimeter, we get that part of it, right? And that would just involve constructing 4 trapezoids, okay? Very similar to this one. They wouldn't all be level, but they'd be symmetric. So, it turns out that the rate that you're going to get between 3 and 4 centimeters is the same as the rate you get between 1 and 2. Now I'm saying centimeters, it's millimeters, okay? That makes sense? So it's kind of neat that we can do that kind of analysis. Now, this course is, related to business and related to life sciences and social sciences and all kinds of things, right? So this would kind of be an example from life sciences. Population models also, and you have that in some of the homework, okay? Our goal this week is to be able to interpret, okay? So we're going to take a look at a couple of interpretations. Well, we don't really have a lot of time, but we'll talk about it. And we talked about some interpretations last time, okay? The other thing I'll say, let's look at this thing. It's getting a little long, but it's not bad. What you would really do is you would figure out this flow rate as a function of R to get the actual flow rate, because this is only an approximation. To get the actual flow rate of the blood, you do an integral. Okay? So I'm just going to make a note. It's fairly straightforward to figure out what the integral would be once you understand all this. Okay? If you figure out this flow rate function as a function of R, okay? Then we might actually do that next time. The integral corresponds to area, and of course you're familiar with the area interpretation of an integral. Had a good course before this, right? So you're totally aware of that. And you're going to become even more aware of it, and you love it. Okay? Integral corresponds to area, and slope corresponds to the derivative. I'll say here the integral of flow rate per unit of area function gives us the flow in volume per unit of time, because this is volume per unit of time. And you can visualize in terms of what all these things mean, why that is. If you understand why this is what it is, okay? So we already know what the integral would mean. We would just have to figure out what the functions are, okay? That means we would have to figure out what our linear function is for the velocity And then we know that we only have to multiply that by 2 pi r. Okay? Then if we had a few more minutes, we could actually write that out. We might pick up on that next time and just see what the integral is, and also see what the trapezoidal approximation we get by doing 1 millimeter increments is. See how close the approximation of our trapezoidal graphs is to the actual rate of flow. Okay? That'd be very interesting and very informative interpretation and use of integral that should illuminate some things. Now, the problems that I don't need to say this on camera.